Yeah. Hey, everyone. We are here with Brandon Ramirez. He's one of the co-founders of Graph Protocol. He'll be doing a talk on gas-efficient mechanism design. Once he starts talking, can you guys just confirm that you can hear him? It should be an awesome talk.
Thanks a lot. Yeah, so hey, everyone. Thanks for giving me part of your Sunday. She said, I'm Brandon Ramirez. I am co-founder and research lead at The Graph. And today I'll be talking to you about gas-efficient mechanism design. And why are we talking about this? Well, obviously, Ethereum gas prices have skyrocketed over the last 12 months by more than an order of magnitude. I think in the past month, we set a new record where miners earned $500,000 in fees over the course of just a single hour, which highlights not just that gas is getting expensive, but also that, as you're designing these mechanisms that are designed to live forever, you kind of have to think of these changing dynamics over time. So what we're going to be talking about today is not anything specific to Solidity or low-level Solidity optimizations. We're not going to be teaching you about how to choose your protocol incentives. I'm going to assume that you have goals and mechanisms that you've kind of already chosen in terms of like what the economics of your protocol are. What we are going to talk about is how to think about algorithm design in the crypto economic setting to implement the incentives and the mechanisms that you've chosen and what constraints that can put on your design process. And to do that, we're going to go through some common problems that we've come across while designing the graph that we think are general enough that they can be kind of illustrative of some of the decisions that you'll be making when you go through this process yourself. So just to kind of compare, where this is coming from, when we do algorithm design in the traditional setting, one of the things, or a few of the things that we kind of pay attention to mainly are like time complexity and space complexity. So given the size of your inputs, how much memory or how much computation, what do you expect an algorithm to take? And our sign-off criteria for whether an algorithm does its job or not is usually based on like functional equivalence or approximating, some functional criteria, right? In the crypto economic setting, we still care about things like time complexity and space complexity, but we care far more about economic equivalence or approximation than we do about functional equivalence. So that's something that we'll see in the examples, that sometimes something that's completely functionally different, can be a good fit economically, given your design goals. Another thing we focus on a lot is decomposition, right? Because blocks have, a finite amount of computation they can do in a single block. So we're always looking at ways we can, break things down to be done across, multiple blocks, potentially be called by multiple actors. And that's kind of the final thing that, I'm going to be paying attention to a lot here is like, who is the designated caller and payer for these computations? So this is something that in, the traditional setting, most computations in like a client server model, you're just kind of running these things on the back end and you're not really thinking about, all right, who as an actor is triggering these computations and actually paying the economic costs of running these computations. And you'll kind of see that leads us to like pretty different places than maybe we would end up in the traditional algorithm design setting. So problem number one that we're going to work through today is just distributing tokens, which is like a pretty broad concern if you're building apps in the blockchain space, right? It might be either you're doing some kind of airdrop or you're doing, you have an incentive that pays out, a group of users in tokens. A naive way of approaching this, just to highlight the differences to traditional algorithm design would just be to do it in a for loop, right? Like you've got, a set of recipients, you've got a set of payout amounts that you want to send to those recipients. You loop through them. It's kind of an O of N complexity with respect to the number of recipients. Can't really get much more efficient than that in terms of time complexity, right? You're just iterating over each one once to do the transfer. And yet in the blockchain or the crypto economic setting, this really wouldn't be a optimal solution because Potentially you're iterating over thousands of recipients and paying the gas cost for every single one of those ERC20 transfers. And maybe that doesn't fit into a block, or maybe you don't want to spend thousands of dollars to implement this mechanism, or maybe it's a mechanism that needs to keep playing out over time. And so the fact that it's just being triggered in a single loop doesn't really let it get triggered by multiple different users, given different conditions. So let's go through a few ways that we might rethink the kind of naive solution there that would work fine in a traditional setting. One solution that's become kind of popular is called a Merkle Airdrop. So this is particular for the case of trying to airdrop a bunch of tokens to users. And the way that this works, roughly speaking, is that you have a contract on chain that stores a payouts root. It's a Merkle root of a Merkle tree of amounts, where basically if you put in the address of a user, you can see the amount that they're entitled to receive as part of the airdrop. Just a quick recap. I'm sure most of you are really familiar with Merkle trees at this point, but each node, each inner node and the root node is basically a hash of the left and the right. And so you can form a proof that an amount is included in the root of the payout tree just by providing the leaf node and then the branch leading back to the root node, which includes the siblings at each level that's in the branch. This is way less efficient in terms of time complexity and space complexity, right? We've introduced this complex authenticated data structure. Now to collect your rewards, you have to provide this, essentially a cryptographic proof that I'm entitled to this reward, right? You have to supply the Merkle proof. And yet, in many cases, it's actually preferable because it allows us to decompose the computation into each individual user claiming the fee for themselves. So the user will be paying the gas costs of this Merkle proof to claim their reward. And it lets it happen over any number of blocks, right? So it's the person paying for it is the person who benefits, and they can do that, at the time that it suits them. One downside of this approach, obviously, is that it's kind of static. It implies, or at least the airdrop use case is more about initializing a large token supply to a set of users. In your mechanisms, you might have something where you want to pay out to a group of users kind of in a more dynamic or ongoing basis. In that case, the Merkle tree would either not be a fit or incur significant costs, which we'll touch on later. Another solution that you might approach is paying out into a pool. And this one, these ones I particularly like to show visually, just because I think it helps build an intuition. So when you're paying out into a pool, you can kind of think of this line, as representing the price of buying into the pool. And you can think of the x-axis as being, the shares in the pool. So as you're moving along, this line, which is, at the y-axis value that corresponds to the, the price per share, what you're really doing is you are depositing tokens into and out of this function. So let's say, for example, as you move from 8 to 10 on the x-axis, it's really the integral of this function that defines the amount of tokens you're putting in. So it would be 2 times 6 would be the amount of, because we're at y equals 6. The neat thing about this is that you can you can put tokens directly into the pool without changing the allotment of shares. So I could shift this up to, let's say, y equals 8. And so now, even though I paid 2 times 6 to get into the pool, if I go back down to, if I remove those 2 shares in the pool, now I'm actually getting more tokens out than I put in. I'm getting this kind of, 2 times 8 tokens out. The nice thing about that is that, again, the computation is decomposed, right? It's really the individual, when they're withdrawing their shares from the pool, that they're actually claiming their reward. And it's lazy, right? So like you're only ever, on an ongoing basis, the mechanism you design only ever really needs to put tokens into or out of the pool. It doesn't even need to think about, are there 1,000 or 10,000 people in the pool? All your mechanism needs to do is put stuff into the pool, and then the participants in the pool can kind of lazily claim the rewards, again, at a time that suits them. We actually use this in the graph for our delegation rewards. So you can imagine that an indexer has any number of delegators going to them, and to pay out rewards to delegators, you don't want to do that, one by one. So we actually have a delegation pool that looks very similar to this, that allows us to do that efficiently. A slight variation on that approach that I think is very useful and neat is a similar pool, except where shares are allotted on a bonding curve. So this is, pretty common in a lot of protocols. You'll see shares or tokens minted on a bonding curve, where the price of minting a new token is defined by this, either quadratic or some other polynomial function. And that presents some difficulties, right? It's not as simple to reason about just adding and removing from a quadratic function as maybe it was from shifting a line up and down. But intuitively, you can think of all the parts of this curve as working the same, right? The price is determined by the function. If you're moving tokens into or out of the curve, you're really paying or withdrawing the integral of that delta, right? So if I'm moving from here to here, I'm paying the orange region is what I'm paying to get into the curve. A trick that we make use of in the graph is actually using the Bancor formula to pay out rewards into the curve. And so for those of you that aren't familiar, the Bancor formula, instead of defining a curve by a specific, quadratic function or polynomial function, all it does is define a reserve ratio. So it defines, the ratio of basically the area under the curve to, the market cap, which would be like this larger rectangle, which I think I have here. So like this green square rectangle is the market cap. The area under the curve is the reserves. For a quadratic function, that ratio is going to be 1/3. The nice thing about that is, using those kind of invariants, the Bancor formula lets us add tokens into and remove them from the curve as well. But we mainly use them for adding into the curve. You preserve the general characteristics of, the curve. It's still a quadratic curve, and you preserve the share allocations. But now, if someone were that same user who had bought into the curve, that orange region, withdraws their tokens, they're actually getting a lot more out. So very similar dynamics to the pool, but with a much more complex way of allocating shares in that pool. And that's actually something we also make use of in our curation market. So we have these bonding curves in our curation market, where curators mint shares, and the way that we distribute the rewards they get from curating successful subgraphs in the graph is by paying out those rewards into the curve. This is by no means the whole design space, by the way. I mean, there's so many different ways you can use curves. Uniswap, has curves with 2 different types of reserves in them, and they kind of do like sort of a combination of these methods of bookkeeping. But these are just sort of the general concepts that you should be familiar with. Finally, another possible solution for paying out rewards, if your goal is to incentivize a certain behavior, is to just pay out the rewards probabilistically, right? Like, very simple example that most people are familiar with is like Bitcoin. Obviously it's a layer 1 chain, not a protocol built on chain, but you have all these miners competing to, get the block reward. Well, that's just paid out probabilistically. They're doing this work of securing the chain, but not everyone gets a reward on, every time step or on every draw. The way that you would implement this in a, on a blockchain smart contract environment would be using something called sum trees. So we looked at another type of Merkle tree earlier, some trees are just another Merkle tree where, in addition to having the hash of the left and right children on each node, inner node, you also have the sum and of the values below it. And what that lets you do is, if you can think of those values in the leaf node as being like a number of chances of winning, so like a number of tickets, you can kind of just do a draw at each level in the tree to get down to the winning leaf node. And so you can kind of think of drawing as being in like O of log n time with respect to the number of nodes in the tree. A number of protocols use this technique. A lot of like lottery protocols. One of the costs of it, the reason that we didn't choose it for ourselves, was that you do have to maintain this Merkle tree, which does come with some costs. So these solutions aren't one size fits all. You kind of have to think about what's determining my chances of winning. How often does that thing update? What are the specific requirements for the mechanism you're designing? Some other caveats that I want to just kind of call out when you're switching from a deterministic payout to an expected payout, right? One thing that's really cool about that approach is that it really does highlight the what I was saying earlier about how it's really economic equivalence or approximation that trumps over functional equivalence. So economically, many would argue that paying out something probabilistically, kind of keeps the same expected value and is equivalent, even though functionally, it should be very clear that it's not functionally equivalent. Even economically, we should be aware of when we're making approximations that are, just that, approximations. There's other dynamics that those might impose in our system. So, one example of that, going back to the Bitcoin example, is that it's estimated that over 13% of ASICs will never mine a block in the lifetime of the ASIC, right? So if you think about what that means for a second, is that even though, like, let's say I'm an individual, miner, and let's say I'm mining with one ASIC, there's a very real possibility that I never get a reward, right? And so what we've seen in, kind of proof of work blockchains is that can be a centralization vector. It encourages people to join, mining pools. I'm not trying to make a judgment on whether that's good or bad, but you should just be aware that it will, or it has the potential to change behavior. Another thing to be aware of is that expected value is not always equivalent to expected utility, which is a notion that's become popular in economics and decision theory for modeling what drives a user's behaviors. And so just because there's a probabilistic payout that has the same expected value, it doesn't mean that the expected utility would be the same, right? They might have a concave utility function that has diminishing returns, assigned to the value of money. Equivalently, there's another branch, kind of more recent movement in economics, kind of removing the ergodic fallacy, where they're replacing expected utility with expected time average growth rates. If you want to learn more about that, I recommend looking up like Ole Peters' Ergodicity Economics. But equivalent result arises there, where expected value of a single draw is not the same thing as the expected time average growth rate of your wealth, for example. And just kind of reiterating that going from small to large payouts can change other dynamics. So one thing that we actually ended up having to look at while we were evaluating the probabilistic payouts was that we realized that suddenly it became a lot more attractive to front run one of our mechanisms, right? Because when we had everything that was paid out in these like very small increments kind of continuously, there was never really like an opportunity where it would have been like even worth the gas costs to try and front run. But when you switch, let's say, from 10,000 smaller payouts, over a period of time to like, 10 really large payouts, now other dynamics can enter, your constraints, where you need to worry about, okay, well, is there a potential to front run these payouts? And that'll vary a lot just by, the way that you're applying these. So it's hard to generalize. All right, so the next problem we're going to look at is computing continuous rewards. This probably is the mathiest section that we're going to look at, but so just bear with me. So an example here, it's hard to contrive something that's going to be relevant to all your protocols. So I'm just trying to start with something very simple. The example here that we're looking at is that you have some reward function that you're trying to implement where the proportion, the rewards that a user gets is the amount of signal, signal can be anything, over the amount of total signal times the total amount of rewards available, right? So this fraction on the left is just determining their share of rewards. Again, the naive way of approaching this would just be to put this all in a summation, right? And like you say, okay, at every time step, I'm just going to compute this function, right? Like you came with your economic requirements of, for some reason, this was the way you wanted to pay out incentives, and you're just going to compute that every block. You're going to do it. And I say naive, really, it's impossible. I mean, you're never going to get anywhere this way, because if you have any amount of users and you're not going to be able to compute this reward on every block. And not only that, like who would be triggering that computation on every block, right? Is the user going to call into the blockchain on every block and say, hey, make sure you compute the rewards for this round? Obviously not. But one thing you can do, and actually one thing I want to focus on this is when you're looking at your reward functions that you design like this, and especially when you have a summation like this, it's important to think about, for the different inputs to this, think about the state in a few different ways. So I like to think about at what frequency will these inputs be updated, and then who is actually updating these inputs. So in our case, the signal for user J is modified only by the user, right? The total signal is modified by all users, and the total rewards, in this example, is being set at the network level. And so not only are there different groups that are changing these inputs, but they're also changing at very different frequencies, right? You can kind of trivially assume that the total signal is updating more frequently than the individual signal. And similarly, if the total rewards is a network level parameter, you could argue that that's changing very infrequently. So the solution that I recommend for this is something that I call accumulator memoization, for lack of a better term. And it basically just relies on looking at the thing that's changing the least frequently, moving that outside of the summation. So instead of the summation representing the rewards for all time, now the summation is just representing rewards during a time period where the signal is being held constant. And now the reward function reduces to signal times this accumulated rewards per signal, right? That's the thing in the summation. We have total rewards over total signal, and then we're just accumulating over that. And the interesting thing about that is that that thing on the right side of the function, that applies to all users, right? Not just user J, but user, all the other users that are supplying their own signal. So now we can kind of memoize this accumulator, just update it every time the signal is updated. But then when it comes time to pay out a reward, we only do that when the user's signal itself has changed, right? When it stops being a constant. And that's paid for by the user at the time that they change that state, right? So I know this is a little abstract, but this is a pattern that you'll see all the time. We've come across it a bunch. There are more advanced versions of this. I'm going to probably go through this a little fast just because I'm running short on time, but just wanted to point out that you can also compose this pattern. So you can actually have multiple levels of memoized accumulators and multiple levels of like input states that change at different frequencies for different sets of users. So I'm gonna just put this up here. You can rewind and look at it on YouTube. But I just wanted to make that point that this is it's a pretty powerful pattern that that you can apply in a lot of different ways. A last point on a last example for computing continuous rewards is that a lot of times you'll see reward functions that kind of have this form. This is totally based on the incentives or mechanisms that you've chosen for your protocol. But you might have something where you have, rewards are kind of accumulating, by this, where at each summation step it's being, multiplied by some greater power of a number, right? Or you might have, on the bottom function, you might have something where it, rewards are increasing, just times, times a number, right? So these are, respectively, these are finite geometric series and finite arithmetic series, so functions that have this form. And you don't really need to know how to solve these because there's widely available functions for looking at the sum of a finite geometric series or finite arithmetic series. If you're interested, you can prove it through mathematical induction. But I only make the point just so that you're aware, like when you see this in your mechanisms, or you stumble across this, there's a good chance that instead of having to actually do this sum, there's some neat closed form solution that lets you get the sum of that series without having to compute this reward continuously at every time step. So that's just a really useful thing to look out for. Last one, I'm going to try and get through this pretty fast, but a really common problem in work token protocols like the graph, where users stake to perform some amount of work, is how to allocate that work. So in the early days of work token protocols, it was very common to do that on chain, right? Where you would look at the amount of stake that a service provider has, and you would say, okay, well, based on the amount of stake, we're going to probabilistically choose someone to do a certain unit of work, right? Which means that every unit of work needs to go through the underlying blockchain, which is a non-starter for a protocol like the graph, where we're doing, billions of transactions per month. I'll just point out that a really naive way of trying to solve this would just be doing the exact same thing on like an L2 chain, right? Just say, okay, well, it's too slow for a blockchain, but we'll just apply a faster chain. And that might get you further. It certainly wouldn't get you to the performance requirements of the graph, but I want to point out just that I think this mechanism in particular highlights that, thinking outside the box and moving away from functional equivalence, you can actually get something that has your desired results while being economically equivalent. So this is a technique I learned from the folks at 0x. They do something similar for their market maker fees. But basically, what you can do is you can have fees sent into a rebate pool rather than directly to a service provider. And then you can have the service provider claim a rebate from that rebate pool. And the function that determines the share of the rebates that they get is their share of contributed fees to the pool at a given time step and their share of total stake at a given time step. And it just so happens that when you do this in equilibrium, the optimal behavior is to basically stake and contribute fees in equal proportion, right? So if you're contributing a fourth of the fees to the rebate pool, you want to have a fourth of the stake in the network. You can kind of see graphically that when you plot that ratio of your share of stake to share of fees, that it's this kind of concave function, and you can kind of intuitively see that, like, if an indexer, let's say, or this is a service provider, you take the average of their two rewards when they're out here in a kind of non-optimal staking intensity. It's going to be that average is going to be on this dotted line, right? If you do a weighted arithmetic average, it's going to be somewhere on this dotted line, and that's always going to be lower than the point on the curve, which is to say that it's in their benefit to trade with one another until they are staking in proportion to the amount of fees they're contributing in the network. If you plug values into that function I showed you earlier, you can kind of see this intuitively, right? This service provider on top, who's basically an equal proportion on his share of fees and stake, is getting all his contributed fees back in the rebate pool, so he's getting the same share of the rebate pool back. But you have these two service providers here that you can kind of think of as those two dots that were further out, that even though they're collectively contributing 0.6 of fees to the rebate pool, they're getting collectively some share less than 0.6 of the rebate pool back. And so this is just really interesting because, it basically incentivizes the service providers to end up at this optimal, allocation that you want without actually forcing it through some algorithm that's run on chain.
Brandon, so we are out of time right now. Do you have any last thoughts?
Yeah, I'll just leave this slide up here. This was the last slide anyways. But just final thought is that, scaling mechanisms is about more than just blockchain scaling. As I said before, good time complexity in the traditional algorithmic setting doesn't guarantee a gas efficient mechanism. Economically analogous mechanisms can be functionally different. Who pays for our computation is just as important as how much it costs. And I recommend placing the burden of computation on those who it benefits, right? Those who have an economic incentive to make that transaction happen.
Awesome.
And that's all. Yeah, thank you guys so much for your time and attention. If you have any questions, you can find me on Twitter. DMs are open, and yeah, happy to keep this conversation going.
Awesome. Thanks, Brandon. We're going to transition to our next talk now.